Central Time. My name is Dr. Matthew Richardson, and I'm your host for today's stream of CosmoQuest Astro Office Hours. All right, let's go ahead and do the usual. But as you can tell, today we'll be talking about the distance to the moon, or at the very least, how to calculate it. All right, so let me first go ahead and verify that I am actually streaming. So just give me one quick moment. You know what? I'm actually going to make a modification. Let's see. Put this here. I don't like this angle. We're going to do this. Oh no. Let's do that. Boom. Right there. I like this better. Kind of center. Oh, nope. Wrong way. Let's center it. And I think that that's a lot better, actually. All right. So let me go ahead and first verify that the stream is working like it should be working. Chrome. But until I get that up and running, or at the very least the verification process done, I hope everyone is doing well today. Although at the current moment I can't see your comments. I can't see the replies to that statement I just made, but nevertheless, I really do hope that everyone's doing well today. Come on, Twitch. There we go. All right. It looks like it is working. So I'm going to go ahead and pop out the chat. Oh, hey, Peter. We have thunder snow. Oh, I'm sorry to hear that. Yeah, here in Clarksville, Tennessee, the weather is beautiful now. Although I think it's supposed to rain at some point, but I mean, I'd take rain any day over snow. Oh, I'm sorry to hear that. Hopefully it's not too loud to the point where you can't hear me. Hey, Guido. All right, let me quickly say hi to everyone here who's here in chat. Hey, Susie. Hey, Binary Ablaze. Hey, Electrical Skateboard. Hey, Jutlander. That is a new name. Welcome to today's stream. And hey, Peter. All right, guys. Let's go ahead and just jump right on into it. So today we're talking about calculating the distance to the moon. All right. So the way in which we do this, or the way in which we're going to do this, is kind of like how we did. It's really unbelievably cold today here. Oh, God. I typically don't think in terms of Celsius. Nevertheless, I know that anything below 0 degrees Celsius is freezing. And it didn't go over -5 degrees Celsius, so it's really cold there. I'm kind of sorry to hear that. But yeah, that's... I can't stand temperatures like that. And here in Tennessee in general, I don't think it ever really gets... At least it never feels like it ever gets that cold. I don't even know if it really gets that cold. But yeah, that's pretty cold. All right, so I have to set a few things up because we're going to kind of do the same thing. We're going to do something similar to what we did in our last stream. So we're going to be using stellarium to help us out with today's calculation. All right. So I have this set up for being able to jot down, notes and calculations. -3 is the max there. Golly. Hopefully it warms up sometime soon. Alright, so we're going to have to set up Stellarium. Let's see what sort of scenes I have going on here. Scene 2 is a browser. We will need that, definitely. So let me go ahead and open up a browser and assign this browser to this particular scene. Alright, so let's do Google. There we go. I think everything should be set up already. And then lastly, we have our Stellarium. I think I've upgraded my Stellarium software. So let's do this. Let's move out of that. Let's look at the OBS software. No, it did not notice that version of Stellarium. All right. There we go. All right. So as you can tell, it looks a little bit elongated. See if I can somewhat fix that. Okay. And now let's do this. All right. That looks a lot better, far more circular. However, I'm noticing something. It looks like you guys cannot see all of the crosshair there. In fact, maybe it's just my OBS software, but in the center of that circle, or within the circle, do you guys see a cross or just a vertical line? Guido, you and me both, man. Stellarium is a great piece of astronomical software. But can you guys see a okay, you do see a cross. Okay, perfect. All right. Because with my view of it, all I see is a vertical line through the circle. Okay, perfect. All right, let's go ahead and jump into it, guys. So, we're calculating the distance to the moon. I need a picture. I need a picture, but I want a picture such that it'll give us a general idea of what we're doing, but I don't want to give away specific values. So we're going to go ahead and go to Google. All right. Oh. Let's do this. I seem to have already done this before. Perfect. All right. Well, let's do this. Angular size of moon. Wait, I don't want to give this away. Wait, no, that's wrong. Let's go to something else. Images. I don't want to give that information away. Well, you know what? Even if I do give it away, at the very least, we can verify. So anything that doesn't give it. Sure, we'll go with this, actually. Even though it gives a physical answer, that's cool. We can still verify it using Stellarium. Right. Perfect. All right, I'm going to zoom in on this. Okay, let's make sure that you guys can see this. You can. Perfect. All right. So the general idea is that as you view the moon from the surface of the Earth, In this picture, that would be the little eyeball in the lower right portion of our picture. There's going to be this angular separation between both ends of the moon that we're basically looking to calculate. That would end up giving us its angular diameter, which of course would correspond to a physical diameter. But at the very least, we need this angular diameter to be able to calculate the distance to the moon, as well as the physical diameter of the moon. All right, but and this picture actually doesn't really give what I think I'm looking for. Maybe I could find another. Nope, that's not it. Sorry guys, give me 1 second. I'm trying to see if I can find something that would be more of a this is better actually. So in this situation, the opening angle at the left-hand side of the image is kind of where we're starting, right? We're here on Earth, and we're looking out towards some object towards the right, where that object in this case would be the moon. And so there's going to be a relationship between the angular value of theta and this at the far right edge of our image, this distance d, which actually corresponds to the diameter of the object that we're looking at. And of course, the lowercase d is what we're going to be solving for in this case. So let's sorry, my brain is kind of freezing on me right now. Where do I want to go with this? Let's go ahead and go to Stellarium actually, and see if we can go ahead and calculate this angular this angle theta, which of course we already know to be it put it as 31 arc minutes, I believe, which kind of corresponds to roughly a half a degree. And I'm going to be working in degrees here because I don't like working in terms of like arc minutes and arc seconds. All right. So Stellarium, there we go. Let me quickly look at the comments here. All I know is that the moon has a pixel diameter of about 1,000 on my 14.1 megapixel bridge camera at a 35 millimeter equivalent zoom of 840 millimeters at most. You can actually see it change size on the images depending on the distance. So yeah, what we're going to end up first doing with this is, and given that, I mean, we are, again, we're a group, we're huddled together, out in the cold. For some of you guys, it really is cold where you're at, but we're huddled together outside, and we're looking through our telescope, and we want to be able to determine the angular diameter of the moon using the telescope. So the very first thing we're gonna want to do is, of course, find the moon within our within the eyepiece of our telescope. Yes, keep the cold away. All right, but I do have a funny story because I told you guys last time a while ago when I was doing some observations with my class to calculate the diameter of the Earth. We end up going to, and actually, yeah, I can tell this story while I'm setting this up. We end up going to two locations along a almost perfectly north-south road somewhere in Nashville, or in the outskirts of Nashville. And when we did this, I believe the instructors had already gotten permission to be at the two locations because I believe they were on someone's property, but I think it turned out to be that one of the locations we didn't actually have the permission to be on. And so, and I happened to be at that location. However, the other group was perfectly okay. And so, while we're doing our observations and stuff like that, using our theodolites to get the elevation angle of Polaris at our location, I think it was like 3 cars drove up. It was like a truck. It was no 2 trucks and a car drove up, and the guy quite literally gets out of the vehicle. Like all of them get out of the vehicle, and one of them has a shotgun. And so immediately when I saw the fact that one of them had a weapon, it was like in my mind I'm thinking like, oh, this isn't going right at all. This isn't a part of astronomy. No, I was scared out of my mind, actually, to be very honest. But to make a very long story short, the teacher, the lecturer that was there with us at the time, he handled the situation. He explained to them what we were doing on the property, and they just happened to see us with all these devices, and then looking at the fact that some of us was wearing some of the Vanderbilt. That's the school I was taking this course at. We were looking. We had our Vandy stuff on. We're outside. It's the middle of the night. It's cold. Yes, a shotgun. Only in America. but yeah, and so, but to make a long story short, he ended up handling the situation. He explained to him what we were doing, and let him know that we were just out there, just do measurements to the star. And they looked around, and they could tell like we weren't like of any sort of threat or trying to like do anything to the property or anything. And so they were just like, okay, do what you have to do, and then get off the property. And so, but I think that was the only experience. You said TWO shirts, 2 shirts? Would it, oh, you mean you're wearing 2 t-shirts? I'm with you. But yeah, that was the only time during any of my courses that it was like a very weird moment. A weird moment that could have been potentially very, dangerous if the people that we were talking to like weren't reasonable. All right. So we need to find the moon. So the very first thing I'm going to do is I'm going to set the clock for us. And I've already picked the location. It doesn't really matter what location you do this at. The location I chose was here at Clarksville. And I'm setting the date and time to today for tonight at 9:00 p.m. All right. So time is now set. We need to now, of course, find the moon. And I would try my best to like move the telescope such that it can find the moon, but this is going to be too difficult. So we're just going to go ahead and search for the moon. And it moves us to the moon, which wasn't that far away in the first place. Perfect. All right. So now that we've found the moon, our objective. So I don't want it to track the moon, so I'm going to get rid of all that information that we have. So we're centered on the moon, and we want to be able to find out its angular size. Well, the problem. I'm sorry. Give me a quick second. I have to make sure my laptop's charging. Oh, that's weird. My laptop doesn't seem to be charging, which is worrisome. Oh, there it goes. All right, it's charging. All right. So the way in which we're going to end up doing this is we're basically going to allow the disk of the moon to pass through one of the edges of our field of view, and we're gonna keep track of the amount of time it takes for it to do this. So let's go ahead and do that, and then I'll go ahead and continue on with why this is important. So I've centered our telescope onto our moon, and now we need to just allow it to just drift away from the center and towards one of the edges. So I'm going to go ahead and start the clock. Let me look at the comments and see if there's anything. All right, let's allow this to go ahead and just drift now. So I'm going to go ahead and press play. And so we're going to end up needing to note at what point in time the leading edge of the moon hits the edge of our field of view. So I'm actually going to get really close up on the laptop so I can keep track of this. So the moon is moving towards the upper left. And so we can find that leading edge. And it looks like it's hitting at roughly, okay, I'm just going to call it at 21, so at 9 p.m. and 30 seconds is what I'm going to call it. So I'm going to write this information down. Let's pause for a second. That's the beautiful thing about this calculation is that we can pause. We can pause our simulation here. Simulation pause. There we go. So let's go ahead and navigate over to our tech document. And we're going to put in here, let's see, what was that? So start time, or time at which leading edge of the moon intersected our field of view. All right. And so we have a start time of, let's see, what was that? I think I said it was at 21 and 30 seconds p.m. All right. So now we need to go ahead and continue to now watch for when the moon disappears completely, or when that the trailing edge ends up hitting the exact same spot within our field of view. So let's go ahead and go back to Stellarium. I'm going to go ahead and press play. All right, it's moving. I could speed up the time, but if I speed up the time, I'm worried about the fact that I might end up missing it. So I'm just going to let it go ahead and just play out. But while it does it, I can quickly look at comments as well. You know, a third arm would be handy at times. What? Toys R Us is going out of business? Is that what you mean by that, Peter? Wow. Or are they going to like simply just close down their they're in the UK? It might be because a lot of people like to go online and shop now. So are they completely closing down, or is the situation that they're just going to simply um, shut down all their stores, but still do online business? All right, we're almost close to that point in time where the entire disk of the moon is gone. Okay, it's almost there. It's almost there. Boom. I'm going to call it at 2:50. All right. So same hour, but at 2 minutes and 50 seconds into the hour. Let's go ahead and pause this. There we go. So we're going to go back to our tech document. All right. And we're going to put that the end time was at 21 hours, 2 minutes, 50 seconds. Which now means we can calculate an elapsed time. And I'd use a calculator to do this, but that would be extremely lazy because it's just simply 2 minutes and 20 seconds. Is that right? 2 minutes, 20 seconds? Which is the equivalent of 2 point, so I'm going to convert to decimals now. 20 out of 60, 1/3. So 2.33. Is that all right? 3 repeating. This is how many minutes it was. All right. So there is our elapsed time. Now, why is this important? Well, it's important because the moon is moving, right? It has some sort of angular velocity to it. Well, given that it has an angular velocity to it, and we've just we calculated an elapsed time for the entire disk of the moon to move through a single point, we can now calculate how much angle the moon subtends given that amount of time and given its angular velocity. But the question is now, what is the angular velocity of the moon relative to us viewing it through our telescope? And so I'm going to put here angular velocity of moon while viewing through telescope. And I'm going to go ahead and begin an equation here. But before I actually show the equation for it, I'm going to ask you guys, because we're part of this group. So let me go back to comments. Hey Adam. Hey Bill. Welcome to today's stream. So we're talking about, oh wait a second. Let's comment this stuff out so that I can actually tech this up. So guys, today we're talking about calculating the distance to the moon. And the general picture that we're using to do this calculation is, let me go ahead and OBS, switch scenes. We're using this general image where in the image, with this image in particular, we're at the left-hand portion, or better yet, let me scroll up actually. So, Safari. I'm going to scroll up. This is the actual image that I want us to have in mind. And I see that my face is kind of taking, you know what, I'm just going to block that actually. That's what we're going to do. Boom. This is the actual image that we're using. We're here on Earth, where we have our eyeball here. Imagine it's a person on Earth looking through a telescope actually. And we're looking at the moon, and we're looking to find the angular separation between the two edges of the moon in which those lines intersect. And so the way in which we're doing this is we've used stellarium, and we've basically allowed the edge of the moon to pass through a single point along the edge of our field of view. And we've calculated the elapsed time, shown here. We've calculated the elapsed time for how long it takes for that edge, or for the disk of the moon to pass through that single point. Now, the reason why this is important is because we now wish to find out what the angular, displacement is from for the moon passing through that single point. And we're going to relate all of this information, that is the elapsed time, and the fact that the moon has some sort of angular velocity, to be able to figure out what that angular displacement is. But my question to you guys is, right, and I'm going to go ahead and write out the equation. So let me go ahead and switch to my tech here. Oh wait, this is, so let me see something really quick. Can you guys see everything here? Yeah, you can, okay. Looks a bit small. Let me make it bigger. That might be a little bit better. All right. So angular velocity of the moon while viewing through telescope. We can go ahead and just write out the equation for angular velocity. We get that omega equals, oh Matt, what's wrong with me? Which one? I'm trying to think of which equation. Right. I want to use delta theta over delta t. So fraction, because there's more than one equation for omega. There's the linear velocity that the object has as it rotates around something, divided by its disk. Yeah, we're just gonna use I'm going way too far with that. We're gonna use delta theta over delta t. Where delta t, of course, is going to be our elapsed time that we've calculated. So let's go ahead and typeset that. That's our equation. And we're going to go ahead and solve this equation for delta theta. It's still a fraction. No, it's not. It's incorrect. It's just basically omega times delta t. All right. And so that's the equation we can use to figure out the angular velocity of the moon while viewing it through the telescope. However, we know delta t, but we don't know omega, or do we? And so my question to you guys was, how do we determine omega? Does anyone have any idea? If I miss saying hi to you, I apologize. But let me quickly go through the list really fast of people that appears to be new. Hey Adam. Hey Bill. I believe I've said hi to everyone else. If I haven't, I apologize, guys. And Michael T. Mayer, actually. That's weird. I'm seeing your comments, but you're not showing up in that list of people that are a part of the chat room. But no problem joining late. I hope that you were able to catch my re-explanation of what we're doing right now. So we're attempting to determine the distance to the moon. The key information that we need to calculate this distance is the angular, not the angular velocity, but the angular displacement, or the angular diameter of the moon. And also we need to know the physical diameter of the moon. Now that information we're just going to grab off online. Even though we could calculate that as well, I'm just worried that we'll run out of time. So we're just probably just going to grab it off online somewhere. Well, my main question right now is that we're trying to calculate the angular diameter of the moon. We've used stellarium to figure out how much time it takes for the disk of the moon to pass through a single point. So we've calculated that elapsed time, shown there to be 2.33 minutes. But now the question is what is the angular velocity of the moon? Because we need that information to figure out the angular diameter as given by this equation here. And so I was asking you guys, what do you guys think about being able to calculate doing some electrical work? I see, Michael. That's cool, man. Let's go. I don't want to work in radians. So let's go ahead and do this. Do the omega in terms of degrees per unit time. Or I mean, we could do it in radians per second, but are you, Peter? Are you asking me, is omega the last thing we do? So the field of view for this in particular is going to be, let me quickly pull it up so that you guys can also see it. And I believe my face is covering that information, so I'm going to scroll down. This is the field of view information. So it looks like here it says 82 degrees is the field of view. So going from one edge to the other, we're seeing an angular displacement of 82 degrees. However, what we've done in this situation is we've allowed the moon to move, we've allowed the disk of the moon to move through a single point in our field of view. Or we've allowed the diameter of the moon to move through that single point. So if I were to recenter back onto the moon, so I'll go ahead and do that now. Let's go ahead and find the moon. You'll notice here that the entire disk of the moon is within our field of view. But basically what I've allowed to do, the moon to do, is drift out of the field of view of our telescope. And basically the leading edge of the moon that first leaves the field of view, I've noted that time, and then I've allowed the rest of the disk of the moon to move through that point until the trailing edge passes that point, and noted that time as well, to get me basically an elapsed time. And so to figure out the angular diameter of the moon now, all I would need to know is what is the angular velocity of the moon. However, as Michael noted earlier, if the situation were that you had a telescope set up such that the field of view exactly matches the disk of the moon, you'd automatically just know what the angular diameter of the moon is. But in this case, because our field of view is bigger than our than the disk of the moon, we'd have to do it this way. Let me go back to comments. Oh wait, you guys are saying something else. Let's see. 31 arc minutes. Ah, wait a second. We're assuming that we don't know that it's 31 arc minutes. Oh, I see what you're saying. You can do it from field of view. You don't need to worry about the size of the moon. So let me look at your equation that you have there, Bill. Let's see. 31 arc minutes divided by the field of view in arc minutes. Okay, yes, I see what you're saying there, Bill. Yeah, that should work out just fine actually. That would give you omega. But yeah, in this situation, we're just gonna assume that we don't know omega. But there is another way you can calculate omega though, right? The other way in which you can calculate omega is the fact that the Earth itself is rotating, right? And so, because you know an elapsed time, you can use the Earth's rotation to be able to figure out what the angular displacement of the moon is, or the angular diameter of the moon is, excuse me. So omega is actually just the Earth's rotation in this situation. Or I think it's exactly what Bill points out earlier. That's another way in which you can do it. That's actually pretty cool actually. But then again, it assumes that you know the angular diameter of the moon already though. All right, let's go ahead and do it, guys. I hate it when my brain moves too slow right now. We need to go ahead and go back to our tech document. In this case, we're going to go ahead and set omega to be the angular velocity of the moon. I mean, of the Earth. Excuse me. So our omega is going to be equal to, and again, I want this in degrees per unit time. So we're going to use the fact that the Earth moves through an angle of 360 degrees in one day. But given that our angular or our elapsed time is in units of minutes, I'd want to put the answer or the unit of time in terms of minutes. So I think I could do this 1 day times 24 hours times 60 minutes. And guys, check my math because I make mistakes at times. So 360 divided by, and I'm using my calculator on my computer to do this. 1 times 24 times 60. And that gives me a value of 0.25. And this is going to be in units of degrees per minute. So let's do it like this actually. Per min. And I'm going to actually look up what is the LaTeX syntax for degree. Oh, dash circ. All right, that works. I think I can just do this. And let's see what this looks like. And I believe this is it. All right, so 0.25 degrees per minute is the angular velocity of the Earth, and that's what we're going to end up using for our calculation above, or our calculation that we have for the angular diameter. So I'm just going to go ahead and copy and paste that information really quickly. So back to angular velocity of moon. And what we should end up getting is this. So we know that omega is going to be 0.25 degrees per minute. And we know that delta t is 2.33 minutes. Let's go ahead and typeset this and see what it looks like. Make sure that it, all right, that's good. So now we can go ahead and calculate what this physical value is in units of degrees. Let me make sure I'm not missing any of the comments. Yes, that's right. The Earth does go at a slight angle. But we've accounted for the fact that the Earth goes at a slight angle, right? We took the leading edge of the moon within our field of view, and we used that to kind of form that line. But wait a second. So Peter, are you saying I did something wrong? If so, let me know, because I don't want to get the wrong answer here. So delta theta and actually I can't remember what that angle is actually. What the orbital plane of the moon is. Okay, thanks, Peter. What the orbital plane of the moon is versus Earth's plane of rotation, not around the sun, but its intrinsic rotation. All right, let's see. So this value should be, I'm going to go ahead and put this into my calculator. So 0.25 times 2.33. What do we get? So we get 0.5825. So I'm just going to round that to 0.58. So 0.58 degrees is what we're going to go with. Which I believe if we converted this to arc minutes, would be roughly about 31 arc minutes. So I think we're good, actually. So 0.58 degrees is the angular diameter of the moon. All right. So far, so good. All right. Sorry, guys. I was thinking about something really quickly there. Okay, so we're going to go back to our image, and it's 12:51 now, so I need to quickly move through this. We're going to go back through our image. Right. I was looking up the... Perfect. So an angle of 31 arc minutes is roughly equal to what we end up getting anyway. Perfect. And so we could go through the whole calculation and figure out if that's right, but I'm pretty sure it's right. The next step, of course, is now we're going to move along to being able to figure out what the physical distance is to the moon using this diagram we have here in front of us. I'm just going to move myself back down here so you guys can see that. All right, perfect. And so, of course, to use this, I feel much better using right triangles versus using this. But I don't think it would really matter too much, actually. So if we use the right triangle, then we wouldn't take the diameter, we'd take the radius of the moon. And we'd have to split the angle in half. But would it really matter? Let's just do that, actually, because I feel better doing that. I'm pretty sure they do something else here, but we're going to end up taking the radius of the moon, and we're going to use half of the angle to figure out the... So we're gonna do this. Let me quickly get back to the tech document. All right, so we're gonna say now... distance to moon, and we're going to basically use the exact same diagram. So let me go back here so that you guys can see me typing. All right, make this a little bit bigger. All right, distance to moon using the diagram that we just saw. We can basically state that that distance d, or better yet, let's start off with the fact that we have sine of angle theta is equal to the it's opposite of our hypotenuse, so it's going to be equal to the radius of the moon. So r, and I'll put a little like subscript moon. And this should be a fraction over the hypotenuse of the moon, which in this case is our distance d. All right. So I'm actually using the same image, but I've modified it in my brain so that things make a little bit more sense for me. Using small angle approximation, because the angle is very, very small, as we've already shown, it's half a degree. And at small angles, the sine function basically just can be approximated. In this case, the theta is equal to the ratio of the radius of the moon. The radius of the moon divided by the distance d. So I'm going to typeset this. All right. This is what we have so far. And that's incorrect, actually. Now that I've modified it, it should be theta over 2. Sorry about that. Oh, that's so funny. That is so funny. So I'm happy I did it this way now, because it comes to be 2r anyway. So theta is equal to 2r over d, which 2r being the diameter anyway. The physical diameter. And so, oh, that's funny. So I'm just going to replace the 2r with a d. And so now all we're left with doing is solving for the distance d, which all we have to do is interchange the places of the lowercase d and the theta to do this. And guys, I'm going to kind of cheat here. We're going to go online and we're going to get the physical diameter of the moon. Even though we could calculate this, given the information we have about the telescope and stuff like that within Stellarium, but I'm not going to go through all that right now. So we get this equation for the distance, and we're going to go ahead and go online, and we are going to look up what the diameter of the moon is. So let's go ahead and switch our OBS software to a different scene, which shows, yes, there we go, a web browser. Let's go ahead and put in diameter of moon. Sure, in kilometers. All right, the diameter of the moon in kilometers is 3,474 kilometers. I'm just going to copy and paste this. Oh, let's look at that actually. So Bill says, should it not be 0.058? Was the multiplier actually 0.025? Let me go back actually, I'm sorry. Let me look at that. So this is how we calculated omega. 360 divided by the product of 1, 24, and 60. Let me quickly check that. Thanks for looking out, Bill, because I know I make those mistakes at times. Arithmetic is always tricky with me at times. So 1 times 24 times 60. I'm getting 0.25. Is everyone else getting the same thing for this? Oh wait, you guys can't see what I'm looking at. That's why. Sorry. So this is where we end up calculating omega. Using the fact that the Earth makes a full rotation in 360 degrees in one day. And I've converted that one day, which is represented by the value of 1 in our denominator, to units of minutes, so I can get degrees per minute. It's cool, Bill. It's cool. In fact, I'm not a mathematician by profession. I know a lot of people would think like, even though I've come across my fair share. Oh, you saw it. Okay, I'm sorry. But yeah, I've come across my fair share of math, but mathematicians are, and I have a friend that's a mathematician, and they're sick with math. Like it's insane, the stuff that I'm still in awe of when I see the stuff that a mathematician can do with some math, and all the tricks they've developed to be able to do math problems. It's impressive. But okay, so we're good with this value of 0.25 degrees per minute. And again, we end up getting 0.58 degrees for the angular diameter of the moon. So far, we've calculated that the distance to the moon can be determined by taking the diameter of the moon divided by the angular diameter of the moon. So really, I just realized that I would want a delta in front of these thetas here so that it's clear where they're coming from. Okay. I'm sorry, guys. I seem to have lost the ability to modify my tech document. I'm not getting the cursor. What is going on? Okay, there it is. Sorry. All right, I'm going to quickly finish off this problem because I'm seeing that we're running out of time here. So, delta, make these quick modifications. That way we know exactly what variable we're dealing with. All right. And so just to plug in these values now, we end up getting a distance of, so fraction, I think that was 3. Right, you guys can see what I'm seeing. Perfect. So it was 3,474 kilometers. I'm going to put that there. And we're going to divide this by delta theta, which was 0.58 degrees. Just copy and paste that. But wait a second. I can't use degrees. So Michael, you hit the head earlier with saying that we should do this in radians. So I need to convert this to radians as well. So multiply this times, and what's the quickest conversion? I think it's pi over 180. That works. So I'll put a fraction down here as well and say pi over 180 degrees. Because we're not allowed to use just simply degrees in this calculation. Okay. So using this information, now we can go ahead and calculate what the distance is in units of kilometers. And then we'll quickly verify. So we have 3,474 kilometers divided by the quantity of 0.58 degrees times, and this is all in the denominator, times pi, divided by 180. Wow, I'm getting very nice, and I'm gonna round this to the nearest whole number. So I'm getting 343,182. It's actually 181.9, but I'm rounding to the nearest whole number. Kilometers. So that's our calculation for the distance to the moon in units of kilometers. Let's go ahead and verify. And so, we can go back to Google, and we'll put in distance to moon. All right, what do we get? 384,400 kilometers. And if I'm not mistaken, I believe we're close to this, actually. No, we're not close. we're off by a few tens of kilometers, right? 384,343. So we're off a little bit, but of course, there's rounding errors in here. Actually, one of the problems we're going to do one of these days, we're going to include errors. They won't be statistical errors, but they'll be uncertainties, and then we can propagate the uncertainties and see if our uncertainties would include the real value. All right, guys. Yeah, yeah, I agree. I definitely agree with you, Michael. But then I just realized when I got to the end there that I couldn't just simply divide the 3,474 kilometers by 58, 0.58 degrees. So your suggestion of working in radians earlier was like dead on. In fact, that should be a rule of thumb for me right now. Just always work in radians whenever you're doing calculations. Um, it makes life so much easier, especially with approximations for trigonometric functions. Oh well, thank you, Bill. I'm actually happy to hear that. Oh hey, high altitude Cherenkov. Hello, welcome to today's stream. I'm actually quite curious about your name. My username, and I'm just going to say hi to everyone again. You'll see my username is UHE Cosmic Rays, where the UHE is short for ultra high energy, as that's what I did my dissertation in. I was studying the ultra high energy cosmic rays, and so I'm looking at your high altitude Cherenkov, which is actually pretty cool. Oh wait, put the dash circ in the fraction brackets. Oh, you're talking about me reformatting something in LaTeX? Oh, I see what you're saying. Yeah, but that pi over 180, that is clearly incorrect there. But yeah, I think for my next stream, which will be this Friday, 12 o'clock p.m. Central Time. Um, oh, cool. So actually, I don't know. I think I haven't talked about cosmic rays in a while. So this Friday maybe I'll set up a problem, and we'll include errors and everything else with our calculation. All right, guys. Well, the time is now 1:09 p.m. And we've gotten through this problem. I hope you guys enjoyed it. I sure did. I kind of chose the problem like directly before the stream started. So thanks, Peter. All right, guys. Well, until next time, which will be this Friday at 12 o'clock p.m. Central Time. You guys, for those of you in the cold, stay warm or as warm as you can. And for everyone who's here that's new, thank you for joining today's stream. Um, I very much enjoyed the problem and the discussion that we had. Yeah, guys, thank you all. All right, guys. Until next time, I'll see you guys later. All right, guys. I'm gonna stay on the chat, but I'm gonna shut down the stream now. All right. Bye.